Map out the data traffic of a modern enterprise before strict architecture is applied. It looks less like a system and more like a collision. Millions of discrete data points are fired simultaneously across a chaotic network. Placed in isolation, a single Salesforce instance handles its own operations flawlessly. It processes queries, updates records, and triggers internal logic without hesitation. The friction begins the moment an external enterprise resource planning system or a massive data warehouse attempts to plug into that isolated node. They push and pull data constantly, demanding continuous processing attention. Salesforce operates in a multi-tenant environment governed by rigid processing limits. When traffic spikes, concurrent request limits are exhausted, memory caps are hit, and external queries start timing out. The platform forcefully halts operations to protect the shared infrastructure. Integrating external systems cannot be solved by forcing all data through a single monolithic pipeline. It requires selecting precise approaches from the strict catalog of integration patterns. Salesforce defines 6 standard patterns for enterprise integration. Each dictates exactly how, when, and in what format data enters or exits the platform. Successful enterprise architecture requires navigating a matrix of operational constraints, applying the right pattern to the right bottleneck. To categorize these 6 patterns, we need to strip away the noise of the network and build a strict analytical framework. The horizontal x-axis represents directionality. We plot data flow ranging from inbound traffic entering Salesforce to outbound traffic leaving it. The vertical y-axis represents timing. It scales from synchronous at the top, where systems halt and wait, down to asynchronous, where data is fired immediately. The final dimension is payload topology. We must distinguish between moving a single discrete transaction, processing bulk volumes of records, or streaming continuous data events. Our objective is to systematically plot all 6 patterns onto this grid. Doing so reveals the exact operational trade-offs of each approach. Before an architect writes a single line of code, they must plot their required solution within this multi-dimensional space to ensure it will survive under load. We start at the direct transactional layer. This is where systems interact via strictly defined one-to-one point-to-point connections. The most common inbound pattern is remote call-in. Here, an external system acts as the orchestrator, directly calling the Salesforce API to read or write data. When an enterprise ERP pushes a daily batch of orders directly into the CRM database, it uses remote call-in. The inverse is remote process invocation, request reply. In this model, Salesforce becomes the orchestrator initiating the transaction. This outbound synchronous pattern is typically implemented via Apex HTTP callouts. Salesforce sends a data packet outward and freezes, actively waiting for an answer to return. This waiting state creates a blocked thread. While Salesforce waits for the external system's reply, the internal process halts entirely, unable to execute further logic. If the external system experiences network latency or takes 5 seconds to process the request, the Salesforce thread remains blocked for those full 5 seconds. Multiply that by thousands of concurrent users, and Salesforce rapidly exhausts its limits for concurrent transactions, causing systemic timeouts. Request reply provides immediate data dependency. You know instantly if the transaction succeeded. But under heavy load, synchronous thread blocking makes the entire architecture structurally fragile. How do we prevent thread blocking and UI freezing when we need to push data out to external systems? We employ the third pattern, remote process invocation, fire and forget. Instead of holding the door open, Salesforce sends the payload and instantly severs the connection. It does not wait for a response. This is achieved by utilizing native outbound messages or by publishing platform events. The platform delegates the transmission, freeing the active transaction thread to finish its work. If we map these 2 remote process invocation patterns onto our y-axis, we see a stark downward shift from synchronous blocking to asynchronous freedom. Moving to fire and forget intentionally trades immediate transactional confirmation for systemic resilience, allowing Salesforce to push massive quantities of outbound data without risking a single timeout. Discrete single-record transactions cover standard operations, but enterprise architecture must also handle the extreme ends of the integration spectrum, massive data scale, and instantaneous velocity. For high-volume, low-frequency data loads, architects deploy the batch data sync pattern. Using tools like Bulk API 2.0 or Batch Apex, this pattern optimizes entirely for sheer throughput over latency. It processes millions of records in asynchronous parallel chunks. Batch processing handles the heavy lifting, but it is slow. Modern architectures also demand hyper-fast reactive systems that respond to individual changes the millisecond they occur. This requires event-driven messaging. Instead of legacy systems constantly polling Salesforce to ask if data has changed, we replace the point-to-point connection with a decoupled event bus. The payload topology shifts entirely. We go from moving slow, massive blocks of data to broadcasting a continuous stream of lightweight event packets. By utilizing change data capture, Salesforce automatically publishes a notification every time a record is modified. External systems simply subscribe to that feed, completely decoupling the sender from the receiver. Plotting these onto our matrix pushes us to the extreme outer edges. Batch sits in the high-volume asynchronous zone, while event-driven occupies the high-velocity, real-time reactive space. Event-driven architecture replaces fragile, tightly bound connections with a highly scalable broadcasting model, allowing dozens of external systems to react to Salesforce data simultaneously. Modern enterprise integration cannot stop at the server-to-server backend layer. The data must reach the human operator. This brings us to the final pattern, UI update based on data changes. The streaming API functions as the necessary bridge between high-velocity backend event buses and the front-end user experience. Instead of requiring the user to manually refresh a web page, the server pushes data state changes directly to the browser component. Specific fields instantly update without a page reload. This ensures the human operator's view is just as synchronized and decoupled as the back-end databases they are monitoring. We now have a fully populated decision matrix. Mapping the patterns reveals 3 distinct operational clusters. The first cluster contains the point-to-point synchronous connections. They are highly dependent, blocking, and suited for low-volume operations where immediate confirmation is required. The second and third clusters represent decoupled asynchronous systems and heavy bulk processors, optimized for scale, velocity, and protecting system resources. Architects navigate this grid by prioritizing synchronous patterns for immediate data dependency, event-driven messaging for scalable decoupling, and batch sync for pure volume. These 6 patterns provide a precise catalog of tools for managing specific technical requirements against their corresponding strict constraint profiles. Resilient Salesforce architecture depends on choosing the specific pattern required to dictate how a connection behaves under enterprise load.